have observed in the earlier example that in the presence of recursive definition, we have a stuck evaluation. So in order to handle recursive definition, we need to introduce a notion of the recursive expressions. In this case, denoted by the mu x dot e, where e is another expressions. So we need to have an additional rule to unroll this recursive expression or recursive abstraction, sometimes called. So the unroll rule says that whenever you see a mu x dot e, we create a substitution of x. We're going to replace x by mu x dot e in e. So intuitively, basically just unroll the recursive expression by one step and replace the occurrence of x in the e. Example regarding the length function, and we have to rewrite it into the following. So instead of just putting a lambda x as the right hand side of the length function, we have to put a mu g dot lambda x case e of this in front, and we can apply, instead of calling length here, we call g here. So don't worry, this is actually handled by the compiler, but I'm just showing you that after this rewriting, how our system can handle the recursion. Handwritten derivation of the example of our length functions under the treatment of having the recursive abstraction. So now this is our running example where the length function is defined using the recursive abstraction instead of just the lambda abstraction. So overall, this is a let expression, so we apply the let rule to reduce it into the following. We simply replace the length by its right hand side in the body of the let expression. So we obtain the following. We have let y equals to this in and mu g lambda x case x of the pattern matching apply to y, and simply we replace the use of length by this entire expression. And again, this expression is a let binding, so we apply the let rule, and we're going to reduce it by substituting the y by its right hand side, and we obtain the following expressions. So notice that this expression overall is a function application, but however, the first sub-expression, the E1, okay, this one underline, which is not yet in a lambda abstraction form, so we have to apply app2 to reduce it one step further. So to reduce this recursive abstraction into a lambda abstractions, we apply the unroll rule, okay, which is highlighted in the square box here, and we simply create a substitutions about g and replace any of the g in the body here, okay, by the entire recursive abstraction itself. So basically this will be unrolled into lambda x right arrow case x of the pattern matching. In case it's empty list, we return 0. In case it's non-empty list, we return 1 plus original. This curly bracket is the g, but since it's been unrolled once, so this will be expanded into mu g lambda x and then the case expression again, and it's this whole expression applied to the t. Okay, let's call this unroll expression as E1 prime, and now we coming back to our original step. We know that the E1 prime is already in a lambda abstraction form. We can now apply the beta reduction rule here to reduce it, and we replace the formal argument x by the actual argument, which is the list in, and reduce it into the case expressions. And notice that this case expression is having a conditional expression here. It is already in weak normal form. Actually, therefore we can apply case 1 rule here, and we search for the matching pattern. Obviously the first sub pattern doesn't match, and the second sub pattern will match because it is catered for a non-empty list, which is matching with the shape of our conditional expression. And we create a substitutions that replace all the pattern variable, in this case h by the head of the list, which is 1 plus 1, and t by the tail of the list, which is 2 plus 2 cons with empty list. And this substitution will be applied to the right hand side of the pattern clause, okay, which is 1 plus this mu g whole thing applied to t. And notice that the only t that is substitutable is this one, but not the inner one, because this inner one was actually not free, was actually bound by this pattern clause. Okay, so we want to replace this one. So therefore we have this expression. Okay, and this expression overall is actually a op operation. So since this guy, I mean the one is already a constant, so we have to further evaluate the second operand of the plus operator, so we call the op2 rule. This is a subderivation of the op2 rule where we try to reduce the second operand. Okay, notice the second operand is actually in this form. Okay, apply this recursive abstraction applied to a list consists of 2 plus 2 cons empty list. Then same strategy, apply the ab2 rule because this is not yet lambda abstractions to unroll this mu g thingy into the following. Okay, we just basically replace the use of g by the entire expression itself and put it here. And now we can apply the ab1 rule, which is beta reductions, to replace the form argument x by the actual argument, this list with 2 plus 2 const empty list. And then now we have a case expression here. And again, we apply the case 1 rule because this is weak normal form. We search for the pattern that's matches. In this case, it's matching this one. So we create a substitution about h and t again. But now in this case, h will be substituted by 2 plus 2 and t will be substituted by the empty list. And we apply this substitution to the right hand side of the pattern clause and replace this t by empty list. So we have this one again is an op expressions, and we're going to apply the op2 rule here, and this will eventually triggers another ab2 and unrolling, and by applying the lambda abstraction into the empty list eventually give us a 0. So the whole derivation will stop here with 1 plus 0, and don't forget that in the earlier slide we have another 1 plus in front, so the total will be 2.